Thank you so much for inviting me. I apologize that I couldn't be there in person. I kind of really was looking forward to it, but yeah, things came up. So I'll try to share my slides now. Okay. Okay. This is not the first one. Let me just move back. Okay. Okay, well, thank you again for your introduction. And yeah, I really look forward to discussions and even panel session despite of the time difference between Montreal and Valencia. And I think the topic of my talk today is kind of precisely aligned with the theme of the conference about how can we predict AI behaviors, even if not completely, like what can we do, what can be kind of the best effort to do so in terms of predicting performance, predicting potentially unexpected changes and novel behaviors that can emerge. And how can we also make sure that we can build those systems in more kind of democratized way, not just kind of allow them to be developed at a few industrial labs, but let people in open source AI communities and in academia also kind of be able to compete in this rapidly growing field. So I'll tell you about all these three parts of the story. But first, yeah, I want to kind of start with the ultimate goal that many people are talking about, kind of achieving the artificial general intelligence and what exactly it means. And to be honest, it really depends on people you talk to. And people sometimes argue because they define things somewhat differently. Some think it's like superhuman intelligence. Some think it has to be something with consciousness and so on and so forth. But we can actually go back to the more practical definition of artificial general intelligence as a broad, versatile, multitask kind of intelligence that would be in some sense similar to what humans can do in terms of being able to learn during their lives to do so many different things, even though you might not necessarily be champion in chess or Go in the world. You can learn those games, but you can also learn to play musical instruments, and you can do like many useful tasks. So OpenAI definition at high level, characterizing such systems as highly autonomous systems that outperform humans. Oh, I would say at least let's see if we can perform at the same level first. At most economically valuable work, well-read, useful tasks. So the system is multitask, general, broad, and those tasks are useful. And if you think about this idea about generalization, it actually was always there as an ultimate kind of holy grail of the whole field of AI and previously even statistics and machine learning. Because in statistics, as you know, when people are trying to fit curves to a cloud of points, essentially they're trying to see if that curve will predict or extrapolate well to the unseen points coming from the same data distribution. In machine learning for a long time, people were also looking at this type of a generalization to IAD kind of samples, presumably from the same distribution. And that was like the topic of most of the classification work in machine learning. More recently, people started pushing the boundary towards out of distribution generalization when the data experience certain kind of domain shifts, task change, and things go a little bit out of the, well, distribution on which the model was trained on. And many related kind of subfields of machine learning intersect with this idea of out of distribution generalization, like transfer learning or meta learning or continual learning. There are different kind of settings, but the goal is roughly the same. You want to learn systems that eventually can do many different tasks, and those tasks may correspond to very different distributions of data and also different distribution of kind of objectives that the system need to achieve on those data. Recently, literally kind of in the past couple of years, we are all experiencing what one can probably call neural scaling revolution. The advent of large-scale, pre-trained, unsupervised systems that serve as a basis for various recent advances that we kind of observing in terms of all the ChatGPT and similar models like taking the world by storm, and all the generative models, well, Stable Diffusion, Midjourney, you name it, DALL-E. Also, kind of generative AI is being kind of achieving the results that it was never able to achieve just until recently. So what is going on actually here? Because, I mean, the field of AI tried to achieve the high level of generalization and all this kind of type of human-like generation of text and images for a long time. But I always like to kind of remind people about so-called bitter lesson by Rich Sutton. That was kind of a brief position write-up that he wrote in 2019, saying that look at the whole history of AI research. It started with kind of trying to put our knowledge into systems in very direct way, like rule-based systems, expert systems. And then with more compute, those systems became obsolete, and more generic kind of systems like just universal neural networks with a lot of compute, with a lot of data, essentially won over all this specialized kind of rule-based systems and so on and so forth. And this essentially was going on. So the compute becomes more available and cheaper, and therefore the methods that kind of were generic but just didn't have enough power, not enough compute to show kind of good results, becoming prevalent in the field. And the whole history of deep learning is a good example of that, essentially. It's also example of scaling compute and scaling data and then scaling deep network models. And it's important to kind of keep in mind that focusing maybe on simpler generic methods that with advent of compute can solve your problems is important, because maybe you shouldn't be wasting time on kind of more myopic goals of building some improvements due to putting too much of our knowledge. You should work on the methods that will scale well. So, but to know that models scale well, you will need to be able to predict their scaling laws. And examples go on, like in chess and other games, people started with systems that would be very specific to the game, that would incorporate the rules, the intuitions and heuristics that people developed. And later on, all of them were kind of outperformed by generic massive deep search and self-play, for example, and Go and so on and so forth. So examples go on, but the bitter lesson was bitter because essentially what's kind of reminding people that a lot of work went into putting all this specific inductive biases, specific knowledge, which maybe was a bit too specific. And what won historically was generic methods, well, deep learning and search, and maybe generic architectures without too much of the specificity built into them. And essentially, the lesson is maybe we shouldn't be focusing on putting too much of the final result of the evolution into those systems, but we may actually want to develop systems that can evolve in a sense like we did, not the end result of that. So kind of a second order inductive biases, so to speak. And well, where we are with kind of this bitter lesson right now. So we see that what is state of art and what is taking the world by storm are generic transformers that are behind an attention mechanism, which turn out to be extremely important because it allows one to really choose a small potentially number of relevant things out of, say, large context. And now we have all this kind of recent state-of-art chatbots and generative models, and I can go on and on just like talking about them, but you probably all know like what's happening with ChatGPT, with Bing, and with all its rivals So the field is accelerating at like exponential speed. It's kind of started and was outlined a couple of years ago in a paper from Stanford called Foundation Models, because it was a paper in 2021 in August, and it was just right after the, advent of GPT-3. So essentially GPT-3 kind of started this whole era of like scaling revolution. And the idea was that instead of doing what people used to do in machine learning before, like training specialized systems that would be optimized for particular tasks like classification for specific types of data, you pre-train in unsupervised way or self-supervised way a very large model with generic architecture like transformer on very large amount of very diverse data. And essentially what's going on, if the data are sufficiently diverse, like, I don't know, you collect the text from all of the internet, or you collect like some incredibly large amount of imaging data, then this diversity, the amount of information in the data is in some sense a good sample of what can possibly like happen, like say with language. And then if the model is large enough, has capacity to incorporate this kind of large amount of information, then essentially you get pretty good model or the distribution of how things are in that particular modality, or as it turns out later, they can actually generalize to other modalities as well. So they manage to extract high-level concepts that seem to be quite generic, no matter what modality you're using. And jumping ahead, I'm talking about papers like Transformers Universal Compute Engines that show that you can pre-train on language, but with minor modifications, you can adapt the system to images and so on and so forth. So that's why people kind of call them foundation models, because those models can serve as a basis for adaptation and other applications on top of them, because they serve as essentially a knowledge base about what's happening, what the distribution of the data is. And again, I can go on, and this list is just very beginning of 2020 when the GPT-3 was released, but like in May, end of May of, I think, 2020, followed by Clip, which was image to text, then DALL-E, text to image, then Copilot for code generation, and then Stable Diffusion last year, and ChatGPT also last year, and so on and so forth. So basically those foundation models keep popping up like mushrooms after the rain, and at ever increasing speed, because more and more people are getting excited about that and kind of get into this AI race. And if you think about that, it's essentially an autoregressive model, the original GPT-3 and the kind of subsequent versions. It's just basically trying to predict the next token given the window of the previous tokens. The major difference is not the change in the architecture, but rather change in the scale of both the model and the amount of data it was pre-trained on. And that change comparing to its predecessors is orders of magnitude. As you probably remember, GPT-3 was 175 billion parameters, while the closest to it previous versions were definitely much smaller than that by like 2 orders of magnitude. And as I was saying, what was essentially happening and what was claimed to fame by those systems is that this is example of Clip, pre-trained in unsupervised way on multiple image data, and then generalizing zero shot or out of distribution to new data sets, which were quite different from what it's seen before. And it was outperforming like state-of-art specialized systems by far. And essentially that is kind of the gist of this large-scale pre-trained or foundation models. They are able to generalize to previously unseen tasks and novel data in zero or maybe few shot. That's precisely an element of this kind of generalist AI that we are all kind of trying to build. So the classical plot from the old GPT-3 paper shows how the ability of the system drastically improves with its scale. And here is essentially how the accuracy on particular task changes with the number of samples in the data. And you can see that once the model size jumps from the less than 2 billion to 175 billion, the curve of the improvement in performance becomes much more efficient. So the system really starts performing much better on the same number of examples in the context. So that's how scale matters, essentially. And so on and so forth, the dependence of performance, not just on the size of the model, but also amount of the compute that goes into training such model. And those different curves, also from the GPT-3 paper, show essentially validation loss for different models at different number of parameters corresponding to different colors. But they all show that essentially you observe that the best performance is following what's called power law, or the straight line in log-log plot, essentially. And then there was this kind of, by now, classical paper by Jared Kaplan and his collaborators from OpenAI. Jared Kaplan is a professor at Johns Hopkins University in physics, but also now co-leading Anthropic, as most of you probably know, focusing not just on building capabilities of systems, but making sure that while doing so, we keep an eye on alignment with human values and measure it in different ways, and so on and so forth. I will mention it later again. So scaling laws, the classical scaling laws, the first kind of paper, was essentially showing that if you consider 3 key variables on x-axis, it's either compute or dataset size or the number of parameters. And if you essentially look at the dependence of the performance, in this case it was test loss, as a function of that key variable, then you observe your power loss that I mentioned before, which are actually surprisingly simple dependencies between performance and the kind of variable of interest. So in these plots, essentially what they mean, if you take the best, if you fix, say, compute, but you can vary the data set size and number of parameters of the model the way you want to achieve best results and plot those best results, you will get this type of a straight line in log-log plot. Same goes about fixing data size and not constraining or not bottlenecking the other 2 variables. It's just different kind of slope of the curve, but essentially they're all power laws. And the holy grail of the whole scaling field became how do you improve scaling? How do you improve this exponent of the power law that would correspond to improving in the slope of how fast the loss kind of decreases given the key parameters. The interesting thing about scaling, one can ask, why do you need scaling laws? Well, first of all, if you know those scaling laws, it's essentially investment tool for machine learning researcher, because you know when you will have more compute and data, which method will win, and therefore you can invest in that. And this is another example from different paper comparing visual transformers with classical convolutional networks like ResNet. And you can see that at a relatively small number of samples, or kind of, at 10 million, you see that, as you would expect, the convolutional networks are outperforming those transformers. And convolutional networks were state-of-art in the field of image processing for a long time. And they are essentially example of those inductive biases where you incorporate what we know about, say, visual system of humans directly into architecture. But then at the larger scale, when the more data become available, and again, I guess you have more compute to utilize this data and train larger models, you see that actually generic architecture of the visual transformer starts outperforming the specific architecture of convolutional network. And this is something very important to know, because that can give you the idea what will work better in the future and what should you invest in if you know that we will get more data and compute will become more available. So as I said, scaling laws are essentially a guiding tool predicting future behavior of different methods so you can choose wisely. It's like investment tool. So, well, the history of scaling laws, of course, didn't start just 2 years ago with Jared Kaplan's paper. It started a long time ago. And there were different attempts to model scaling behavior. And perhaps one of the earliest papers was from 1994 by Karina Cortes and the famous Vladimir Vapnik and Sarah Sola and others. New RIPS 1994, essentially they looked into power laws. They observed power laws as well in much simpler, smaller experiments, but with also neural networks. And the power law is simply, as you can see here, is an expression. It's like polynomial. Essentially, it's y on the kind of y-axis, which is performance, equals constant a times x to the power of b plus another constant. So we kind of use this notation to denote like several types of functions that people try to use historically to model performance at scale in neural networks. And this is like the snapshot from that paper, where essentially they were making same point I was just mentioning, and I was showing with those visual transformers versus convnets. So this is more of a hypothetical example, but argument is precisely the same, that if we don't yet have enough compute, or basically this compute may be developed in the future, but we do want to know what method, if we have several candidates, will be more promising and will stand the test of time, we need to study scaling laws, because even at the low scale, like you don't have to have large compute and maybe very large data set, but if you can predict the trend, then you will know that in the future, one method will beat another method. And that's important to know, because then you will invest that compute in the more cost-efficient method. Essentially, it's the same point was made in that paper, just like it's being made in more recent ones. And they did observe power laws in the performance of like very small neural network. In that case, it was like well, three-layer network, 110 and 10. And interestingly, as I said, to the best of our knowledge, it's one of the first papers where power laws were observed and used to predict performance of deep nets. More generally, later, I mean, papers started coming up and studying scaling, like 2017 paper by Joel Hesnes and others. And they showed in that paper how the performance scales with amount of data. So essentially, they showed the power law, especially in particular regime, in the particular range of the training for just the data being x-axis. And they also showed that in general curve can be like more expanded than just power law. Power law is a middle regime when you're actually effectively learning. But before it starts, there may be very slow learning due to insufficient data, like on the left, small data regime. And then eventually, when your system learns pretty much everything it can possibly learn about the data, and you hit what's called irreducible entropy, or in classification world, it was called Bayes risk, then the performance asymptotes at certain irreducible error, and that's kind of the third regime. You will see similar type of curves that combine regimes with power law in between in a few minutes. Then there were other papers following up on this work. There was this paper by Jonathan Rosenfeld and his colleagues. And essentially what they did, they applied the power law functional form to, in this case, not the data, but model size dependent scaling. So there were all these bits and pieces. And then Jared Kaplan's paper essentially added on top of those kind of observations that the power law also applies to compute as x-axis. And then the three plots that you've seen were compute, data, and model. But then the interesting thing started happening, which went beyond power law behavior. And that's what people initially were struggling to kind of model and explain. This is another kind of famous plot from the original GPT-3 paper, where on particular task, arithmetic, as turns out, this type of the discrete operation tasks are often leading to this quote unquote emergent behaviors or quote unquote phase transitions. You see that when the model size, basically the GPT model, was increased, initially it couldn't improve performance on this specific arithmetic task. At some model size, suddenly performance improves and the slope of the improvement changes drastically. So the system kind of starts getting or grokking the problem. And then people observe this type of grokking behavior in other settings. So here it's more, that was paper actually called grokking, also from OpenAI. And essentially they observed behavior in setting where model and data were not changing, but the amount of compute spent was changing. And while they just kept running this training forever, suddenly the accuracy went from practically 0 to practically 1 on training data first, the red curve, and then green curve on the test data, and so on and so forth. And there was this paper last year about emergent abilities of large language models, showing many, many, many more examples of this type of quote unquote emergent behavior, or essentially behavior that wasn't there at lower scale, say in terms of number of model parameters, and then suddenly would take off sharply at some point. And that raises a question. You probably would be interested in predicting such takeoff points, especially if the y-axis is not just the performance of the system, but some other properties that you might be even more interested in, like robustness of the model, truthfulness in language models, or other behaviors of interest. So in order to kind of incorporate these different behaviors, we were trying to see what kind of functional form can capture all of them. And it's mainly work of one of my students, Ethan Caballero, and also Shitish Gupta, and me and David Kruger were kind of co-supervising this work. But primarily, yeah, it's really kind of Ethan's brainchild, because he was searching for kind of universal type of functional form that could capture all of the scaling behavior for quite a while. And essentially, the motivation was like, okay, we want to predict those properties because we want to know what type of approach will kind of get us to AGI first. And there are, of course, multiple approaches, but the one that gets there first will be the one that matters because people will adopt it later. So in a sense, there might be some more sophisticated approaches, but if you get there with purely more compute and scaling more generic models, that's what will kind of persist. And it's critical, again, as I said, to be able to predict how various performance metrics will change when you change certain variables that are your bottlenecks, for example, amount of compute or model size or data size. And those y-axes are not just metrics of performance like classification accuracy or whatever metrics people use in natural language problems, but they're also, more importantly, metrics of alignment, where by alignment, yeah, it's not a precise definition, I agree, but we mean certain correspondence between model's behavior and what people would expect from that model that would be aligned with our values. So you can kind of talk about that. That's going to be a separate long conversation, but even as I mentioned, robustness and truthfulness and other things are important. So what kind of things can be the bottleneck or the x-axis? And we already mentioned that it could be essentially data set size, model size, compute, whatever is being scaled, that is x-axis. And what is y-axis? Performance evaluation metric. It could be accuracy, well, prediction error, it could be the cross-entropy loss, it could be the blue score, it could be reward and reinforcement learning, it could be all kind of other ratings that people were using in the recent literature. And the setting in which we can evaluate it could be upstream, or essentially like the data you train on, and you set aside validation data and measure loss on that, or it could be downstream, that you basically use some totally new tasks on which you evaluate the model. It could be zero shot, it could be end shot, it could be fine-tuned, it could be prompted or not. So there are all these different settings. And as I said, again, to repeat, the methods that perform best at small scale may not necessarily be best performing at large scale. So we do want to see their scaling performance, and it might not be necessarily trivial single power law. So basically the question remains, right? What can be used to characterize this relationship between the quantity being scaled on x-axis and quantity that we're concerned about, y-axis? So this functional form called, well, essentially broken power laws, it was used previously in other sciences and, for example, in astrophysics. And people realized that it's quite flexible form that was able to describe various phenomena quite accurately. And it looks a bit kind of scary here, but essentially it is a generalization of simple power law. And it might be easier just to look at how this type of functional forms would look in the plots. This is just an example showing a specific combination of parameters in that broken power law kind of functional form. It's called broken power law because essentially you see that some hypothetical performance here is described by segments of different behavior, just like in a sense, the low data regime where the learning is slow, followed by sudden transition to much faster kind of learning. And it potentially can be even non-monotonic, things can actually get worse instead of getting better, and then they can get better again. The break between the power laws in this picture can be very soft and kind of, or very sharp. It's all controlled by parameters of the functional form. So that gives you idea why it's called broken neural scaling law or broken power law, because it's combination of segments that are smoothly connected, combination of power law segments that are smoothly connected, basically. I don't know how much time I have, and I probably shouldn't go into all details. You're more than welcome to read the paper. It was just accepted to the CLEAR conference and will be presented, I guess, later this spring. The intuitive understanding of different parameters of this form is given there. And essentially, as I said, they control, like, for example, parameter n here controls the number of breaks, how many segments you're going to see there, right? And the parameter f there controls the sharpness of those breaks, and so on and so forth. So basically, I will not go over all the details, but each parameter here has an intuitive kind of meaning that shapes the performance curve. And what was quite mind-boggling and impressive was empirical results showing how wide this form applies to practically all recent papers showing scaling with respect to either model, data, or compute. And in all possible settings that you can think of, as I mentioned, downstream, upstream, different modalities like vision, language, audio, video, models like diffusion, generative modeling, and like the list goes on. And essentially, I think Ethan keeps kind of considering requests for modeling the behavior of whatever model in whatever setting, and essentially keeps fitting those kind of results into the broken neural scaling laws. And what's most important, it's not just curve fitting. We're testing how well prediction will go if you use this functional form of all these different behaviors, modalities, architectures, and so on. And essentially, yeah, as I mentioned, there are different architectures used here, not just transformers, there are MLP mixers and residual networks and images and text and so on and so forth. So what do we see? Well, first of all, we compare with previously proposed functional forms because besides the power law, people tried a bit more sophisticated forms like M3 and M4 literally last year. And it turns out that the model we proposed, the broken power law, is consistently outperforming in terms of predictive accuracy or extrapolation accuracy all these functional forms on a huge amount of empirical results that we just took from other people's papers and just compared how well we can fit its performance using those methods versus the proposed one. This is just one example. You will see a very long table in the paper containing all those results, and they're all consistently showing that this functional form seems to really get the scaling in all kind of domains and settings. And just to show a few examples, because I mean, the number of examples grows as we speak and being added to the appendix. The black points in those pictures will show the points that we measure, like, for example, in GPT-3 paper, you can go to appendix and see for all 8 models that they tried, how those performed on different tasks. And you can basically take those data, leave aside, say, a last point or a few, and try to predict them by this curve. So the black points are observed ones, given ones, and green will be held out points used for evaluation of how this form predicts or extrapolates. And yeah, the red line will be what is fit to those black points. So basically, here, what you see black points for particular setting. This is training data set size and test error rate on the y-axis. And this is yeah, particular example of the setting that's used there just to give you the idea. The black points are measured performance. Red line is a fitted functional form. And then you see all these green points that are never seen by our model and are very accurately predicted or extrapolated by it in the future. So this is keeps happening for, as I said, so many different settings, for reinforcement learning, for single agent and multi-agent, for diffusion generative models. So here you see green point, or maybe it's hard to see, it's on the far right, the green point being extrapolated to after fitting. Then you see basically the video models, so generative models of video. As I said, you might not see on the screen, but there are always green points at the end of the spectrum on x-axis. Those are the points that the model predicts. So that's most important kind of thing, because sometimes people get confused and say, well, maybe this functional form can fit anything. It doesn't just fit, it extrapolates. And that is quite kind of important to understand and kind of see that it can be used for the extrapolation or prediction of behavior. There are many language tasks, like downstream language tasks. There are even metrics in Anthropic's papers using RLHF, alignment metrics, same story. The behavior is being predicted quite well. And even the results from that paper on the continual learning and catastrophic forgetting. So the list goes on, and I probably just invite people to look at the paper and the appendix if they're interested. But robotics, out of distribution generalization there, the multimodal learning, contrastive learning, all these different papers even for uncertainty estimation, calibration. And there are some experiments with molecules, data sets, and so on. So it's really seemed to be like modalities like audio, even for kind of robustness metrics. I mean, it seems to be doing the same thing. It's kind of accurately predicts those green points. And it does it not just for language, not just for audio video, it's also for programming, when you essentially use your large scale models to do coding, for mass word problems, for sparse problems as well, sparse models as well, not just like the classical transformers. And sparse models are quite popular recently because they promise to be much more computationally efficient and inference efficient. They will be much smaller, and ideally maybe we can all use those models eventually on edge devices. So on and so forth. We have a bunch of those plots which all show the same pattern, that this functional form can extrapolate well, and not just those relatively, maybe you could say, simple example, non-monotonic behavior like double descent or multiple descent. It also captures that, like in this picture, you have a bunch of green points being predicted accurately for non-monotonic scaling. And those most kind of startling phase transitions or inflection points, the most important things, I would say, to predict when behavior changes drastically or emerges. They can be predicted too. There are limitations there. Limitations depend on how close you need to get to that transition and how many data points you will have and how sharp the transition is. So of course, there are limitations to any method, but it's good to know that it is possible. And with enough data points and maybe sufficiently close, you can handle prediction of those transitions in completely like a closed box way. You don't really have any other measurements about the behavior of the system, just observation of its performance. Okay, so bottom line of all that is that so far we see that perhaps a bitter lesson of Rich Sutton was quite relevant, that, yeah, so the methods that can scale well and whose performance we can predict will be probably the ones which will matter kind of later on, and which will kind of persist, then stand the test of time. But yeah, what does it mean for people who want to train such models besides just predicting their performance? And quoting Greg Brockman, the most benefits will go to whoever has the biggest computer. And until recently, the biggest compute was in industry, like OpenAI and Microsoft and Google and DeepMind. And academia was really falling behind because of the compute gap. So the idea was that perhaps we can somehow, by joining forces with open source communities, try to democratize AI and try to get large compute. And just one example and one idea was to see whether we jointly can apply for high performance computing, such as government-funded supercomputers, for example, in United States, Summit, and more recently, Frontier. Summit has like 26.7 thousand GPUs, and Frontier has 40,000 GPUs. Even though we might not catch up exactly with industry in terms of number of GPUs, it's sufficiently large compute that none of the academia or open source communities had before. So we joined forces with some of them, and we keep kind of making more connections, primarily collaborating with Lion and Jülich Supercomputer Center, with Eluter AI and with others. And Lion, for those of you who do not know, is based in Europe. It's kind of started in Germany, but now it's essentially an online international organization that, as many other kind of open source communities that started recently, has the goal of essentially democratizing AI, training large-scale models, like they recently trained several versions of CLIP, and they outperformed the original CLIP from OpenAI, and also providing data sets like the Lion 5 billion points data set with images and text, and essentially making it fully available for research in kind of academia, open source, or for pretty much anyone. And last summer, we applied jointly for this so-called Insight program at the Summit supercomputing facility. And essentially, that was about training large-scale language and multimodal models on this large compute and making them available to basically the AI field. The proposal was accepted, so we got close to 6 million V100 GPU hours to train language models, some multimodal language vision models, as well as what we called, well, more generally, aligned ChatX. So it's an interactive training of multimodal models. Currently it's Magma, but doesn't have to be, using human feedback, even not necessarily with reinforcement learning, but just for fine-tuning. And that is considerably improving performance of system in terms of generating what people would consider more ethical. In terms of scalability, we did our tests. Of course, we saw whether we can scale effectively on this compute, and the results are promising. And essentially, to kind of conclude, because I think I'm probably getting very close to the end of the hour already, what are we trying to achieve with all this AI democratization efforts? We're essentially trying to build what probably could be seen as LHC of AI field. LHC, like Large Hadron Collider collaboration, was an example in physics how joining forces across multiple, say, academic organization and obtaining large-scale compute allowed physicists to really study, like in high-energy physics, process the data from this accelerators. Well, the largest and fastest is currently in CERN, and it's only a very large-scale kind of collaboration could afford to do this type of research. And it seems like if we want to democratize AI, we might need to follow that example. So if we keep going in that direction, we hopefully can build those open foundation models. There is already, say, GPT-NEO, 20 billion from Luther. There are larger models being trained. We're also training some suites of models on Summit, as I mentioned. And essentially, yeah, they can be basis for many, many applications on top, just like right now people are building on top of GPT and ChatGPT and those. But those models will be fully open, like, well, Stable Diffusion, for example, that was trained on stability compute. That's kind of another alternative, either government funded or private funded. But there are many supercomputers in different countries, and there are not yet as many companies like Stability that would be specifically focusing on providing compute for open source communities. And essentially, we want to keep trying to apply for larger resources like that and keep growing this collaboration. So essentially, the LHC of AI will be kind of moving faster and making those large-scale models available for all. So that's kind of our current vision. And yeah, that was extra slide. Thank you so much, and I'm open to any questions if you have still time left. Thank you.
Thank you very much. Perfect timing. So now we have 10 minutes for questions. Who's going? Yeah, we have a question. Please talk to the microphone so that Irina can hear.
Okay, so thank you for your talk. My question is whether or what other kinds of fittings have you considered apart from these scaling laws?
Sorry, I didn't quite hear. What was the
So
first part of?
apart from these broken scaling laws, what other functionals or what other functions have you tried to fit those
Yeah.
those data points, I guess. Thank you.
Okay, so basically there were 4 of them that I mentioned, right? Let me see. Let me go back. So there were, besides just plain vanilla power law, there were 2 more that were proposed in actually 2 papers in the last year, I think. Let me just get the proper slide. They were called here, these ones. So I don't know, can you see my?
You're not sharing now.
I'm not sharing?
No, but
Oh.
maybe you can just read them. And are you going to share the slides after the talk?
Yes, definitely.
Maybe that's if
also, I mean, the functional form, there are 4 kind of competitors to this one. They are also in the paper, but okay, so let me, okay. Can you see them now?
Yes.
Okay, so basically the plain vanilla kind of M2 is essentially the power law that people used. And the M3 and M4 were kind of more recent additions to the family of attempts of trying to model essentially scaling laws in wider varieties. But none of them, unfortunately, could really model the non-monotonicity that I showed, like double descent, or inflection points. So essentially you have like sigmoid-like curve or kind of phase transition like looking. I'm not calling it phase transition per se, because sometimes it is, and sometimes I don't want to go into all the details proving that it satisfies definition of phase transition in physics. But you see sigmoid-like curve with inflection point, and the models M3 and M4 could not really capture well and predict well this type of curves. So that was kind of one of the major contributions of this functional form, that it could handle all these non-trivial behaviors well, whether it's non-monotonic and whether it is having inflection point. Yeah. So that's kind of the competing functional forms that we compared with. And to the best of our knowledge, there were like practically not too many other papers proposing something instead. And in a sense, we were kind of open to the challenge, like if anyone can propose alternative functional form that would have as many or less number of parameters, but would equally accurately capture and extrapolate, we would like to see that. So far, we just couldn't find any. And so far, we couldn't find any particular setting where we would not be able to predict behavior with like sufficient number of points. So that's why there was even kind of a post on Twitter, which was somewhat humorous as well, but the core question was quite serious. Like, it would be really interesting to see if anyone can come up with a better, more concise functional form that can do job just as well, or if anyone can provide example of the model setting and behavior that doesn't seem to be in any way being accurately predicted by this functional form. So if you have any examples of that or come up with those, please let us know. As I said, Ethan is essentially on ongoing basis adding more results to the appendix, asking people about different settings like robustness, like sparsity, and so on and so forth. And so far, nobody was able to provide example that he couldn't handle. So the competition is still open.
Hey, can I ask another question? For the cases where you are able to fit the like suddenly emergent properties, the things that look like phase transitions, can you just tell us more about how that, when does that work? When does that not work?
Yeah,
I imagine it mostly doesn't work, right? I mean, it seems impossible. And
no, it is possible, because imagine if that the actual true form of what's going on, right? So if you get sufficiently, I mean, basically you need to estimate the kind of the curvature of the behavior. So you can predict transitions if you have sufficiently many samples from the curve and are sufficiently close, and transition is not, in a sense, too sharp. The precise characterization, right now it's empirical. I understand, and it would be great to have like more theoretical characterization of what sufficient means. But even in that case, we have another line of work. I didn't talk about it here yet because it's not on arXiv. Remember, this is completely closed box approach. But if it's your system, not somebody else, and you're training it, you can measure what's going on inside. And you can try to predict, for example, grokking behavior by looking at, say, trajectory of the training loss and the validation loss. And you can look at the dynamics of the weights and activations. There are several papers right now that are trying to study and predict when grokking happens. And as I said, we also have work on that. Well, to be kind of at higher level, what we observe, that there are certain interesting patterns of oscillation in the loss function, certain kind of spectral signature that can predict quite accurately whether in this particular run, grokking will happen. So you should be able to predict those phase transitions, not just using this type of closed box approach, but with open box, with looking at the inside of the neural net. I'm pretty sure you will be able to predict many of those behaviors. But again, it's not really yet theoretical study. It is more empirical, but it seems to be working quite often with those limitations: sufficiently close, sufficiently many points, not too sharp of a transition. I think adding those open box measurements like loss oscillations and particular dynamics in the weight changes, there are patterns that are predictive that transition is about to happen. And actually, it's well known in physics and in other fields like neuroscience. There are patterns of high frequency oscillations, say, preceding epilepsy, and some other kind of drastic changes in the state of the system. So we can really borrow from other fields on how people predict phase transitions there. Okay, but that would be, as I said, that would be expanding this with open box, not just closed box approach.
Hi, thanks for the talk. So I assume the parameters are set or fitted for each task or setting individually, but are you working on any models that would predict for multiple tasks or setting at once, depending on some features of the system or of the task?
Yeah, that would be, it's an interesting exercise if you can have same functional form that can simultaneously predict multiple settings. Yeah, so far not yet. So far, each particular setting and particular set of results required its own set of parameters. In a sense, I mean, that was the same thing with power laws in Jared's paper, right? I mean, for GPT, yeah, also depending what is on x-axis, you have a different slope of the curve. You have different parameters. So you may or may not be able to reuse exact same set of parameters for it's an interesting question. Like, what kind of settings can be described by exactly the same member of that family of broken power laws? Yeah, but we didn't yet try it.
I have a question. I have the power to take the turn now. It's related to that question, so that's why I wanted to just to tip in at this moment. I think some of the, probably you get better results when you have a smooth set of points, of course, depending on what kind of inflection points they have and all of that. But for instance, if you aggregate a lot of tasks, then you have smoother curves, and maybe they are more predictable than you just focus on a very single task with you don't have a lot of data, and then you have a lot of peaks. And these probably they are going to be confounding your model in terms to just that there are more peaks, more inflections that there. So in cases where, so the question is, how important is it to have a lot of tasks, and whether a possible solution could be smoothing the points before applying the laws or something like that?
Well, yeah, I mean, indeed. Okay, so in the experiment where the transition was being predicted, That was, I think, our experiment with arithmetic tasks. So you could actually average the results over a very large number of initializations. So, and indeed, that's how you get those smooth, that's how you get a very good estimate of the kind of average performance. And that's why I was saying that the quality of your prediction, of course, will depend on the amount of data points you're using for parameter estimation, right? Yeah, so, and open question right now is, say you're training your system on large compute and you want to predict its performance. What's the most cost-efficient way to do that? Like, how many points do I need? How should I position them? Basically, so I minimize the amount of compute I use to make the most accurate prediction. So this is not yet in the paper, and that's something we're kind of looking into. Yeah, like statistically efficient methods for doing so, which are not just statistically, but also computationally efficient. Because you can ask the question, should I, in order to estimate whether there's going to be transition with increasing model size, should I train, I don't know, 2 more extremely large models, or maybe I train 10 more very small ones, and that will be enough. So those questions are still remain to be solved, to have like very practical and efficient method that you can just like give people, and in whatever settings they know that if they use this approach, they will, at the minimum of compute, be able to predict maximally accurately what will happen with their system. Yeah, so that we still need to work on, and that's an interesting question. And I'm pretty sure there are various ways to do that, because I mean, you will need to balance several factors, right?
Thank you. Do we have another question? The last question, perhaps? Yeah, we have a question at the back. Maybe this can be the last question.
Hi. So does the fact that scaling laws are so universal in this domain tell us anything about how these models are working under the hood?
Yeah, that's exactly the question regarding open box and closed box. So what I described today is completely closed box, because essentially we were looking most of the time not on even our own system being trained, by other people results from different papers. And essentially we had no information about what was learning dynamics and how loss and weights were changing. So that's why I said, I mean, like, just by looking at that, it's hard to tell what exactly is going on within the system. Although if we keep studying the correspondence between patterns in the loss kind of trajectory and in the weight space, and with grokking, people are kind of looking into that. We are looking into that. There are several recent works from MIT, from Max Tegmark's group and his students, and also from Jacob Steinhardt's group. There is a recent iClear paper also looking into grokking specific example and trying to see what patterns there in neural net internals kind of relevant to this behavior. So your question was rather, if we use this functional form, what can we say what's going on within neural network, and can we do any kind of interpretability without even taking any measurements? Well, that's a bit tough. It might be possible if we study well predicting those transitions when looking into neural net kind of measurements. And once we understand that if there are certain patterns that are kind of always there when transition happens, then perhaps if broken neural scaling laws will be predicting transition, we can say that, I don't know, I don't see your network, but I can tell you probably those patterns appearing. So it's a tougher question than probably vice versa. I see what's going on in the neural network because that's my model and I'm running it. And those patterns, like that, the work with Guillaume Dumas and one of my students that we hope to put on archive like anytime, you look at the pattern of, say, the spectral pattern of the loss, and you can pretty much say if this run gonna grok or not. The paper was called To Grok or Not to Grok. But again, it reminds me that we really should put it on archive like yesterday. So in this direction, it's easier to have access to internal measurements and learn how to predict upcoming changes. Doing it the other way around, like looking from outside and saying that if the curve seems to be getting close to some takeoff, I bet I know what's going on with the system. It might be possible to an extent, but again, it will require lots of studies of this correspondence between patterns of loss, weights, and whatever statistics of internal parameters you can measure, whatever is relevant to those transitions, how deterministically it is related, and so on and so forth. And if we have such studies, because right now grokking is only study with respect to compute. There is not much in respect to model size and data size. Well, perhaps people are working on that, but we definitely should work on that. If we have good understanding of these correspondences of internal patterns and external behavior, then it will be easier to say just how well we can predict those. And whether we know for sure that change in the behavior of certain shape of the curve means certain changes in network kind of internal behavior. Yeah, but we really need to kind of study much more these correspondences. So all you saw right now is, yeah, empirical. And yeah, and there is not much even done with model and data transitions, only with compute transitions, like the specific example of grokking. And all those papers I mentioned are mainly considering kind of toyish example that the original grokking paper was kind of considering. Yeah, so a lot of work needs to be done here. That's pretty much the conclusion.